abstractions. I kind of learned that here.
Okay, we'll come back to EE631. How was the first homework? Finish on time? Finally? I think starting from second homework, yeah, you're gonna do more towards ADC, this kind of exercise, technology, exercise. So hopefully it will become real and real. So it will be more approaching, to the circuit design, how you can build your final project. The first homework is more on signal processing, so it's more like probably a lot of you actually forgot what you have learned from the undergrad class. That's normal, right? So that homework point is just for you to bring back all that good memory. Or bad memory. Yeah. Okay. Any question before we proceed? And next time, if I ask you whether you actually need more time, just be honest. Just let me know upfront. Instead of this time, I need to wait until 2 days before, and all of you send me emails. Yeah. Okay. All right. So last week we talked about the static spec on the ADC, and now we are moving towards the so-called dynamic spec. Okay, so dynamic spec means that your input right now can vary a bit faster. That's all it means. Okay, so instead of you look at INL, DNL, you may be sending really slow ramp or very slow sine wave, right? And now we're gonna speed things up. Okay, and as I mentioned before, a common way to test the ADC, just like amplifier or any other analog circuits, we usually like to test with the sine wave, right? So here, exactly the same thing. So we want to send in the sine wave tones and look at the output, and then you do the proper choice. Remember we talked about all that, right? How you choose the F-in, Fs, windowing, and how many points you need for the FFT, right? So assuming that you now understand how to choose all that, this is basically how you judge your final performance. Okay, so you do all this a proper choice of your test signals and how you observe your signals. So this is what you're gonna get, right, at the output of your FFT spectrum. First of all, you do see the huge tone right here. So what is that? Input signal. You see a little bit spreading here. Why is that? Yeah, technically speaking, yes, it's some kind of spectral leakage, but it's not. It's more controlled, right? So this is due to windowing, right? So whenever you see this, they must have applied windowing. That's why you will spread here a little bit, right? If you see a single tone without this little skirt right here, what does that mean? If you see somebody showing, assuming that they are not lying, they say, okay, I'm doing this is the ADC output. You see a single tone here, what does that mean? Exactly, so they do the integer multiple of that input period, right? So they are not applying any windowing, which is fine, right? But especially in the simulation environment, you can totally do that, and then you don't need to worry about this spread due to the main lobe of the windowing function, right? Remember? Okay. So that is your signal. This is your signal, right? What else do you see? You see noise floor, right? So those noise floor is coming from, let's say, quantitative noise. It can be a thermal noise, flicker noise. So basically those noise from the circuits. Most likely it's thermal noise. And then you also see these spikes, right? So those spikes, typically they come from the distortion. Okay, So what is a distortion? Remember INL? What is INL? INL is to define the curvature of your transfer function, right? So typically, if your INL is bad, that usually implies that you're gonna have some tone will pop out as one of the error mechanism. There are many mechanisms in ADC design where you're gonna see these tones. But don't worry, we're gonna tackle them one by one throughout the semester. Okay. So the first spec is called the spurious-free dynamic range. So it basically means that the delta difference between your signal and the largest possible tone. Okay, so this is called spurious-free dynamic range. Basically, it just means that within this range, you don't see any other tones. Right? Between your main signal and the largest tone, in between, you shouldn't see any spikes show up. So that's a SFDR. Okay, that's very important spec. Pretty much in all the data sheet, you're gonna find this. Next, SNR, right? So we from 536A, you know that signal to noise ratio is very important. The first one, we derived this already, right? What is SQNR? So this is signal power over this artificial quantization noise power. It's not physical, right? It's not like thermal noise or flicker noise or shot noise. It's really because of the way that you quantize. Okay, that's SQNR. In real life, real life means that if you are measuring your ADC, can I actually measure SQNR? Unfortunately, you cannot, right? Because all you see, the ADC output, you have pretty much everything, right? Okay. So what you're gonna measure, the SNR, will be the signal power to all the integrated noise power, excluding those harmonic tones. So let's go back to this. So how do I compute the SNR? So first of all, you sum up the signal power right here, right? Next, you sum up all this noise, but you don't include this because this is coming from the distortion. Okay, but you sum all the rest of the noise, and that's your SNR. Now that noise includes quantization noise power and also all the circuit noise. Okay, so it's everything, right? Okay, so here's a question: can SNR higher than SQNR? No way. Okay, so this is, by the way, this is a percentage check. You design your ADC, you know what's your SQNR. If in a simulation, you simulate this, you compute. Okay, yeah, I do exactly like this. I compute the signal power divided by the noise power. If that ever become higher than your SQNR, you better go back and check. Okay, something must be wrong. Okay, most likely your test bench is wrong. That's why you get even a higher number than your SQNR. Okay, THD. So this part will be the same as when you design the amplifier. THD is a total harmonic distortion. So basically, you sum up all the harmonic tones. Okay, so that will be a negative number, right? So the tones supposedly will be smaller than your signal power. Okay, the last one, which is probably the most important measure of your ADC, this is called SNDR or SINOD. Basically, it's a signal to noise and distortion ratio. Okay, so basically at this point, you need to compute the signal power divided by everything else. All right, so let's go back to here. So basically what you should do is that, so here's your signal power, and you sum the rest of the spectrum all together. At that point, there's no difference, so-called distortion or noise, because you should sum everything up, right? That's why it's SNDR. So it normalizes the noise plus the distortion. Okay, so among all this, which one should be the worst number?
The last one,
Last one will be the worst number. Which one will be the best number? That's good enough. Okay. Which one will be the second number? So it depends. Okay. Typically THD, if you have a tone pop out, typically it will be worse. But who knows? Maybe you design an ADC that distortion is so low, even lower than noise floor, then you're gonna see a better THD but worse SNR.
Why does SNR matter if at the end in reality the cyanide is what matters?
Very good question. So he's basically saying that SNDR include everything, right? So it looks like everybody should only care about the number, but not the SNR. Very good question. It turns out that in some applications, they can tolerate the distortion, but they cannot tolerate the noise floor. Okay, and vice versa. Some applications they care mostly on the distortion, but less, sensitive to the noise floor. Okay, so it really depends on your system application. Just some application, is more sensitive to one or the other. That's why, if we define this way, we basically cover the entire space. Okay, so in the data sheet, because you are not just one person for one application needing the ADC, right? There are so many different electronic systems, they all need ADC. So usually they will report all these numbers just so that the system designers or engineers, when they look at this, they understand, okay, which aspect they care the most, and they understand what's the impact. That's very good question. By the way, sometimes people also compute the SDR, so basically inverse of the THD. Okay, SDR, so basically you can guess it's just single power divided by all the distortion power, right? Basically just inverse of the THD. So sometimes you may see people call that. Okay. Next, we're gonna define a very important matrix called ENAB. Okay, so ENAB is an effective number of bits. This is probably the most important metric to characterize the ADC score. So you're gonna hear this a lot. Okay, in the futures, people will care mostly on what's your ENAB. So they wouldn't say, oh, you design how many bits of ADC. Of course, they do care. But right after that, people will just will ask you, tell me what's the effective bits. So what do they mean? You remember that the SQNR equation? What is the SQNR equation? Six 0.02 number of bits plus 1.76, right? What ENAB does is that they say, okay, I know this is artificial, right? SQNR is gonna be your best number. So I'm gonna replace that with your real number. What is the real number for ADC? SNDR, right? They say, okay, yeah, I'm gonna swap out, because this is your actual measured number. So you use this to back calculate what's your effective number of bits. You see that? Okay, so now let me ask you. Effective number of bits versus number of bits, which one is higher, which one is lower? Effective number of bits has to be lower. You have to be worse, right? So that's why in the future, right? So when people ask you, okay, yeah, how many bits of ADC you actually produce or you design, the next question they almost always will ask you, tell me what's the effective number of bits, because what they care is how good of ADC you actually design, right? It's not just the quantization noise that you were able to produce, but also all the noise and distortion that you are able to create. Okay. Of course, you want the ENOP to be as close as to your number of bits, right? You want the ENOP close to your N, right? You design for 10 bit, you want the ENOP to be 9 point something bit, ideally speaking, right? But sometimes, as you can imagine, it's actually really, really hard, right? Especially for high resolution. Imagine that if you do 20-bit ADC, you got to make sure your noise floor at the 20-bit, you got to think about how low that has to be, right? So a lot of times, you just cannot do that. So generally, when N is higher, you're gonna see more and more gap between the ENOP and N. Okay. But if you are lower bits, generally you can typically match this ENOP in number of bits and usually less than 1 bit, usually. Yeah. Okay. Oh yeah, this is exactly what I said here. High resolution ADC, usually ENOP is a lot worse because you are limited by the thermal noise. Okay, there's something also called the dynamic range for the ADC. Especially for high resolution ADC, they sometimes define this so-called dynamic range. The dynamic range definition is a little bit blurred. A little bit like what I told you about this offset and gain error, right? So people actually understand the concept, but exactly how you should define it is a little bit ambiguous. But this is the typical way people define dynamic range. So what you do, you measure your ADC, you keep increasing your V input. So let's say sine wave, swing, the amplitude. If I keep increasing the input amplitude, do you agree that my SNDR will keep increasing? Do you agree or disagree? So I have ADC. Right? So I know that I need to inject a sine wave, right? So I start from a smaller amplitude and keep increasing until I become larger and larger. Do you agree that when I keep increasing from small amplitude to larger amplitude, the SNDR will increase? Why does that increase?
Signal power.
Signal power will increase. What about noise? Would the noise increase also? Because in the end, it's a ratio, right? If it's a signal increase, noise also increase, then you cancel out. Would the noise increase?
Not even proportion.
Not as much. Okay. You think about it, right? So let's say contingent noise, right? Remember, as long as your input is larger than 1 delta, it will be more or less uniformly distributed between plus minus delta over 2, remember? See? So at some point, the noise just saturates, right? And same as circuit noise, right? The circuit noise, for example, 4kT gamma GM, as long as your GM is roughly the same, your noise remains roughly constant. Okay. So by and large, the noise more or less stay constant. And your signal power keep going up, so that's why it will keep increasing. What's the slope here? What's the slope here if I increase the input amplitude? So let's say I increase the amplitude by 2x. How much do I expect SNDR to improve? How many dB? Oh, by the way, I forgot to mention, you should do in dB. If you look at the power, 10 log, right? 10 log base 10 of the SNR ratio, or SQNR or SNDR. So 2x input amplitude, 6 dB, right? Because in power is 6 dB. Very good. All right. So so you should have this slope, right? So which means 20 dB per decade, right? Okay, so it will keep going up, and at some point, you see that it start to plateau. What's going on there? Shouldn't that keep going higher and higher? Why is it that you see this will be kind of a first is slow down, and then become this, and then actually it can go down. Your SNDR would become worse. What's going on here?
Distortion because you go above full scale.
Very good. As I go, the sound wave become very, very high. It may exceed the full scale range, right? So let's say your full scale range is between here to here. What happened to this sound wave? Your head get capped off, right? If your sound wave, I kind of clip the top and bottom, what will happen? If you do FFT, what will happen?
Now, like those tones here.
You have harmonic tones. Okay, if you don't believe it, try it in my lab. Okay. I forgot whether I asked you to do that in the homework. Yeah, but if I didn't, you can try yourself. Okay, sine wave, just clip the top and bottom and do FFT again. I assure you, you're gonna see those tones. So if your tone pop out, your SNDR will go down. If I look at SNR, probably it wouldn't go down as much, right? Because I only consider all the noise for it, right? Not so much on the distortion, right? So you see different metrics will give you different information. Yeah. But SNDR is always our ultimate measure, right? So if you measure that, it should give you the best. Okay. So then you start to define your so-called dynamic range. So usually people, by the way, this is where the ambiguity may come from. Okay, so you may say, hey, this is my peak SNDR. Okay, so from the peak SNDR here, all the way back off to 0 dB SNDR, this range is called dynamic range. Some people don't define that way. People say, no. When you get to peak SNDR, you already compress. So they will look at this and then ideal curve. Then look at if you deviate by 1 dB, and that will be your maximum dynamic range. So you see, so then it becomes a little bit ambiguous, a little bit. But it's okay. In the future, if you see this so-called dynamic range, you just look at what's the definition. Okay, do they define from peak SNDR to 0 dB, and that's the range they're talking about, or they compare it to ideal curve and they say, oh yeah, this is a 3 dB compression point, and you compare it that much. Okay. All right. So even though it's not super clear, but at least you kind of see what they're trying to say, right? So the basic is define the dynamic range as if this is a workable input range. Okay, so maximum input range is, let's say, 1 dB compression point from the ideal curve. Okay, yeah, that's where your maximum input can be. So what is the minimum input you can do? This is maximum, right? Minimum 0 dB means what? Means your input power is exactly at the noise floor. Do you agree? Noise, I shouldn't say noise floor, is noise plus distortion. Right, so noise plus distortion. So basically just when your signal is just right, just like a noise. That kind of makes sense, right? So you say, yeah, what is the minimum detectable input that your ADC can detect? Is it, oh yeah, it's just right the noise or distortion level. Okay. In fact, at this point, you pretty much talk about the noise. Why? I know it's SNDR means noise plus distortion, right? Why did I say that? When your input is so small, you are mostly just dominated by the noise. Because all this distortion usually scale with your input, right? Your input becomes smaller, usually the distortion is not that bad. Remember 536A? Is it true? You enjoy input, large input versus small input, which one has better THD, right? So yeah, smaller the better, right? Usually smaller, your circuit will be more linear. Yeah, so same deal here, right? So here you are right down. This is essentially your noise floor. This point here, essentially is your noise floor. Right, and that defines your minimum. So this really defines your minimum V your ADC can tolerate. Right, and whatever that at the maximum here. So let's say if this is 1 dB down, right, or 2 dB down, or 3 dB, or whatever that people define this, so this gonna define as the maximum B of the ADC. Okay. All right. Last thing, I want to talk about the figure of merit of the ADC. Okay. So this figure of merit was defined to quantify what's your power efficiency of your ADC, right, or energy efficiency. So basically, how efficient that you actually design for your ADC. So the equation here is power divided by 2 to the power consumption, so this is the total power consumption. Okay, so you look at the total power consumption of your ADC divided by 2 to the power of E naught times Fs. Okay, in fact, there should be minimum of Fs or twice the signal bandwidth. For the Nyquist ADC, of course, there's no difference, right? Because Fs equals to twice the bandwidth, Nyquist ADC. The reason I have to write like this because remember I talked about subsampling, Nyquist sampling, and oversampling. This is for oversampling. Okay, so oversampling when your Fs is much faster, but your signal bandwidth is much narrower. Okay, so in that case, you have to use this twice the bandwidth. Okay, so they basically try not to let you cheat, because somebody who said, oh yeah, no, I do oversampling, look at how amazing I am. I make the Fs 10 gigahertz, even though my signal bandwidth is 1 megahertz. Okay, but then when I normalize, I use 10 gigahertz to normalize, and you would think that I'm amazing, but I'm not, right? Because in there I'm cheating, right? I'm just having 1 megahertz bandwidth. Yeah. So this number, of course, smaller the better, right? Smaller the better, right? So basically, given the same enough that you achieve, the same sampling speed, you want the total power consumption to be as small as possible. Okay. So if you look at the unit, this will come down to joule per conversion step. So this is energy consumption. Basically, this is how much energy you're gonna consume per ADC sample. By the way, ADC has how many samples? ADC? If I operate ADC, how many samples do I get? Many, right? It can be infinite. Depends on how long you actually capture. But then, if somebody would say, okay, you take 1,000 sample, she take 1 million sample, and then you say, oh, she consumes this energy, you consume that energy. That's not even fair, because he only process 1,000 sample, she process 1 million sample. So it's not fair. We have to normalize it, right? So we need to. That's why we divide by Fs, right? But even then, it's not fair. Why? Because maybe he designed for 6-bit ADC, but she designed for 10-bit. Right? So every ADC sample, she actually quantizes more levels. Actually, this is a bad example, I should flip. Maybe he designed for 10-bit, so I don't want her to win over you all the time, right? So maybe he designed for 10-bit and she designed for 6-bit, right? So he, even though he consumes more power, but then in the same time, he actually quantizes with more levels, right? So it's not fair. So we need to divide by 2 to the power of ENAP for that reason, right? If he actually designed for 10-bit ENAP, of course you should divide that more, because he actually quantizes more levels. Does that make sense? So this is basically the measure to help people understand how amazing you are, the ADC that you design. I think, period. There's no other reason why you go for this. Okay, so this is basically just an impressive factor. Okay. This initially was proposed by Warden, so that's why you sometimes will hear this terminology, is Warden figure of merit. So sometimes you may hear that. However, as people start to develop all kinds of different ADC at different speed, different resolution, people start to realize the deficiency of this matrix. Basically, the difficulty is that, yes, I understand that you normalize to this number, but how do you fairly compare somebody designing for 10 gigasample per second ADC versus 1 kilosample per second ADC? Even though you say that, oh, Mike, what are you talking about? We already normalized to the speed, right? But depends on how you implement the ADC. It's not always that, oh, all this is speed and power, they scale proportionally. You see, this equation assumes that they scale proportionally, right? But that's not the way how circuit works. If you are pushing the timing very tight, right? Like 5 versus 8. If I say that, oh yeah, this can bandwidth product, I'm gonna ask you to do 1 terahertz. Versus I say that, oh, by the way, just do 1 kilohertz or 2 kilohertz. You can imagine there are a lot more different techniques that you can do, right, to make a difference. So, the first time that when Warden created this figure of merit, his intention is that so I can fairly compare with all the ADC in the world. That was his intention. But over the years, it turns out that they start to fall apart. Okay, so the bottom line is, right now, when you compare this, you compare to the ADC with similar spec. Does that make sense? So let's say you are 10-bit and 1 gigasample per second ADC. Of course, you know, if you compare like 8-bit, 9-bit, you know, around 1 gig, you know, 700 meg, all this number roughly accurate. So you can still fairly compare between those, right? So this is what people are trying to do now. So basically, when you are similar spec, right, then you use this number to more fairly judge. Okay, is my idea better than your idea?
So the limit for like sampling rate is the parasitics capacitance within the circuit. Like you make the parasitics inductance and capacitance relatively small, so you can run at like very high speed.
Yeah, so there will be a lot of speed concern, and so there's no single factors. So sampling capacitor will be one of them. But don't worry, that's the topic exactly we're gonna go over the entire semester.
Okay.
So you're gonna see one by one why higher speed will lead to more power. Why more bits will lead to more power. Okay, so there's no single answer. So that also depends on what topology you are using. But no matter what, I have not seen the ADC to say that, oh yeah, just throwing more bits and all of a sudden the power can go down. I have not seen that, right? So everybody still go up, you know, so all this trend is still correct. It's just a matter of, do you increase like 3x or 2x? There will be some difference, right? So, okay. But you know my advice, right? So if one day you find this go up, and this go down, you know you should talk to me, right? You should talk to me right away. Right? But in general, yeah, so you go up all this, denominators, your numerator goes up. So this goes together. All right, any question? Okay, if not, I think we are done with ADC basics. So we can start going into more circuits. Okay, so the first circuit, the building block is called the sample and hold. Okay, so this is one of the, pretty much the first block that you would design, you know, for the ADC. and there are a few readers. Yeah, so I will upload all those, or you can search yourself, right? So you can, all these are IEEE papers, so you can search for those papers. Okay, so by the name, you know what we are trying to do. We are trying to do the sampling. From the signal processing lectures, how do we do the sampling? Remember, we need to convert from continuous time to discrete time. Remember, what we do is we multiply by what is this function called? These blue arrows is delta function, right? So you multiply by delta trend, right? And the spacing of the delta trend is supposed to be your sampling, right? Your sampling frequency, right? Or sampling period, right? So this time spacing is your sampling period. Okay, so you just multiply by this delta function, essentially, right? You multiply by delta function. And then supposedly you should get these numbers, right? Okay, those points, right? So that's a discrete time point. Okay, and then of course, if you look at multiplied by delta function, supposedly in time, you will go to this value and come back to 0, right? That's the math. Is it possible? It's not possible. There's not such thing in the physical world. It will go up and go down in no time. So this is much more reasonable, right? Do you agree? We call it the zero order hold. So what we're gonna do is that instead of quickly going back to zeros, we hold the value until you take the next sample and you drop to the next sample and then you hold it. Okay. Is this more reasonable? At least compared to before this guy, right? So I think I should plot all these zeros, right? Okay, so certainly a lot more reasonable. Okay, so is this realizable in real life? So remember, every time I intend to sample, I just go to that value and stay. Go to that value and stay. What circuit in real life that I can do this? Capacitor. Would that?
What do you mean by straight?
If there is negative.
That's exactly what I'm hoping that you guys can ask. What does that even mean? Here. What does that mean? It's like cliff, right? It's a 90-degree cliff. What kind of circuit I can do this? Switch. But even if that's a switch, do I go like this?
It will have some time.
You will have some time to go down, right?
Yeah.
So as much as this looks more reasonable, at least visually, right, compared to the previous one, unfortunately this is still a joke. I mean, this is a joke, right? And by the way, even though it's a joke, if you know how to do this, you know who to talk to right away. Right away, right? Right away. Okay, so because of that instantaneous drop of the voltage, unfortunately this is still not real, because in order to have the instantaneous drop, you design the circuit, you need infinite bandwidth. Whatever circuit that you're doing, it has to be infinite bandwidth, and sorry, there's no such thing called infinite bandwidth in real life. Probably not even on Mars, right? On Mars, I don't think you can create infinite bandwidth. Does physics hold no matter where I am in the universe? I have no idea. So talk to maybe physics professor. I think it probably should hold no matter where I am, which planet I'm on. But let me know if you actually found some escape case. Okay, so we know it's impossible. So in real life, we need to do this code, so-called track and hold. Okay, there's no such thing called sample and hold. I know in the future you're gonna hear people talk about the circuit code as sample and hold. but you need to understand you cannot do this. You cannot do, oh, I sample to that point and then hold it. Okay, it's not gonna work. In real life, in the real implementation, this is what's gonna be more feasible. It's called track and hold. So what you can see here is that I'm gonna open up the period called the tracking period right here. So what does the tracking period do? Just look at this. So you are holding, so there's still a holding period, right? So this is from the previous samples. Then what I'm gonna do is that during this tracking period, you see this guy, green? Is there a cliff? There's no cliff, right? That's impossible. So I'm gonna give you some time, so which is tracking time. And I'm just gonna allow you to keep up. You just keep up with me, right? If I'm the input, you just keep up with me. In this case, I need to go up, you just follow me. You go up, and hopefully by the end of that tracking period, you catch up. And then we stop. So hold, right? See, and next time, so tracking period. Okay, obviously you see there's a gap, right? So this guy has to try very hard to catch up. And you hold. And then this one is going down, right? So actually you should reduce. So you should also reduce yourself, so try to catch up. Okay, so this is tracking hold. So in this case, is this equivalent to sampling circuit? Okay, so what do I mean by sampling? Like this. Is this equivalent to I'm sampling at particular spots? Remember, the sampling action is still real. We still need to convert in the end of the day continuous time to discrete time. So it has to be go by sample, right? That kind of makes sense, right? Because the ADC output eventually will become a digital sample. So if you don't convert to analog sample, how do I convert to digital sample, right? So where is that sampling point? Under the track and hold. You see, at what point I actually sample it? Which point? Between
When it catches up to that.
when you catch up and between the track and hold.
Yeah.
That transition time is your sampling point. You see that? So that's why in the track and hold circuit, you still mathematically can model with multiply with the delta function. It's just that where's that delta function? The delta function is exactly the boundary between the tracking and the holding. Okay, so it's now at the beginning, right? You see, look at the beginning, I'm nowhere close to the actual input. Okay, so it is at the end. But other than that, all our math, calculation, expression, they still hold, right? Do you agree? They are exactly the same, right? That, otherwise, why would I bother to teach the signal processing first, you know, with modified with all the delta function, right? So it has to hold. Okay, it has to hold. All right. So it's always, so as I write here, the track to hold transition instant is the one that you actually define your sampling instant. This one, typically we call that as the track and hold circuits. But because in the end of the day, you are still doing the sampling, so actually, probably more often than not, you're gonna hear people call that as a sample and hold circuit. Okay, but it's just that in the future, you know, just make sure you understand. It is not this. This looks to me more like sample and hold circuit, right? Because you sample and hold. Unfortunately, this is not gonna happen. It's more like track and hold circuits, but the track and hold circuits, you still consider that as a sampling actions, right? So people also call that as a sample. Okay, so that's how it works. Nothing else, right? Sounds very straightforward, I hope, right? Other than you need to understand this at the end of the tracking phase, right? To the beginning of the holding phase. That's actually sampling instant. But however, just look at these sampling circuits or track and hold circuits. We need to consider finite tracking bandwidth, aperture uncertainty, sampling jitters, switching distortion, charge injection, clock feed through, hold feed through, droop and noise. Just to name a few. Okay, this is just one sampling circuit. Okay. But don't worry, I'm gonna spend a lot of time going through one by one. One good news here is that it turns out that this sampling circuit or track and hold circuit is not just used in ADC. Okay, a lot of the mixed signal circuits. Have you guys heard about switch capacitor circuits? Switch capacitor circuits. It just comes down to track and hold. All those switch, they are track and hold, and they all have exactly the same design consideration. So even though this is an ADC, I put that as a part of the ADC class, but I'm already teaching you the switch capacitor circuit. Okay, so I will show you some switch capacitor circuits, so don't worry. But in the future, when you graduate, move out of the class, next time you see those kind of switch capacitor, can be filter, can be amplifier, can be anything. Don't worry, you are already covered by this class. Okay, so the design consideration are exactly the same. You know how to deal with them. Okay, just like everything else, let's start from the easiest or the simplest circuit. So let's do this. One switch, one capacitor. So that is our passive track and hold circuit. Okay. So first of all, you see there's a clock controlling this MOS gate. Okay, the clock is the clock that you are doing. So clock, you have high, you have low, high, low. Okay, so let's try to understand this. When the clock is high, what is that transistor? In this case, it's a MOS, okay? A MOS transistor. This is the continuous time input that you're trying to sample and hold or track and hold. Okay, and that's the output of the track and hold. So input and this output. Draw this out. Okay, when clock is high, what is the mode of operation of that switch? So linear region, saturation region, off region. Linear region. So first of all, it's on or off? It's on. Okay. By the way, usually when it's high, it means it's BDD, right? Usually power supply. Yeah. So this, it is on. Yeah. It's just a question of the saturation region or trial region.
Isn't that an MOS?
A MOS, yeah. So when the gate of the MOS is high,
Only linear because it's supposed to act as a switch, so your VDS.
Yes.
yeah. So this will be in the linear region because you really just like on and off, right? Or trial region. Trial region. Okay. So trial region, this transistors looks like a resistor. Do you agree?
Yeah.
In the trial region. What is IV curve only in 536A? This VG or VD, right? That's correct, right? So this will go up and like this, right? So trial region means what? You're here, right? So you look at this slope, it's like a linear slope. That's resistor, right? So it is R. So that's why we call it R, right? Okay. So this, when you turn on, right? So when you're tracking, so this, when you're high, here is the tracking mode. Remember track and hold, right? Track and hold, track and hold. So when the gate of this is high, you are in the tracking mode. Okay. So what determines the dynamics during the tracking mode? You see that? This, your green is trying to catch up with the red. It's not instantaneous. Why is it not instantaneous? You have R, you have a C. RC, we call this as the zero pole, what do you call it? It's like a pole, right? Because it's like a, what kind of filter is this? If you look at the low pass. Low pass, you have 3 dB, It's a pole, right? Pole frequency. Yeah. So you have this RC low pass filter, essentially. So the track and hold circuit essentially is like a low pass filter, right? So okay, so that's why you have this time constant R and C here. So you have a pole frequency right here, or like a low pass filter that determine how fast you can track, right? You can track to your input. Okay, so it's like a low pass filter, right? Like a low pass filter, and this pole frequency is, what is this pole frequency? 1/RC, right? So if this is C, so it's R and C. Yeah, so that's exactly how that works. Okay. So to understand this, of course, we need to understand what is the value of that R, right? R on, right? And this, you know, that's in triangle region, right? In triangle region. Oh, I already said that here. Okay. So if we assume that's a square law device, what is R on? 536A. 1/, so I'll give you a hint. It's 1/. Mu CX W/L, right? That sounds familiar. And what else? 1/VGS minus VTH, right? So what is a VGS? V clock minus being minus VTH, right? And then if the V clock here is just a swing between VDD, then we can replace this with VDD, right? Okay, so is R on constant? R on? B in, what is B in, right? So the ADC, your input can be anything, right? Between, you know, whatever minimum to the maximum swing that you try to do. So unfortunately, this B in is changing. Do you want a high R on or low R on? Low? Because you want to push the pole to be very high, so that what? If you push the pole very high, what happens to this green curve? It gets sharper, right? You want this to be sharper so you can catch up. All right. So when I will screw up in this case. By the way, even though this is very simple, this is actually used in real life. 1 MOS, 1 cap. Believe it or not, actually people do this. So this is not a joke. Okay, I don't do this just because it's easy to analyze. No, this is real. Okay. So when should I worry? When being. So you said that you want R on to be low, right? So when basically the question is that when would make R on to be high, or you won't. When being is higher, right? Because you see when being is higher, then this value will become smaller. In fact, is it possible to cut it down? Because you say it's on, right? You want that to be on, obviously, right? You want to track. Is it possible to cut off that switch? If Vin and it's greater than VDD minus VTH. Do you agree? You're not even on. So basically your R on of that MOS switch will keep rising as your input value become larger and larger.
Can't you put like an amplifier before this to cap out the maximum and minimum B-in?
Typically the B-in was designed by the preceding blocks, so whoever designed the previous EDC block. So yes, you do need to communicate with them. You say, okay, this is my full swing range, right? invert dynamic range, being, you have to perfectly communicate whatever gonna give you that continuous time analog voltage, right? To say, okay, this is gonna be my upper bound.
Can you put a buffer with like the BDD and BSS for like the full something whole like range? So
Yeah, so you will have some kind of drivers, right? Driver or buffers up front. Yeah, and then, but no matter how you bias that buffer, it still comes down to what's your input swing, right? Because if your input swing to that driver is small, then your output come out of it has to be small, right? So it's all end-to-end system design. So you got to work with the previous block designers to figure it out, right? But just with this circuit, we already sense that when V in is high, your R on will be high, right? Does that make sense? How should we solve this problem? Transmission gate, right? You guys learned this in VLSI class. What is a transmission gate? You have a MOS in parallel with PMOS. Why would that be good?
So it's never floating.
So you see, this is R on versus V in. If you look at a MOS only, we just talked about it, right? Your R on will increase, right? As your V in increase. In fact, when you go beyond VDD minus VTH, you're gonna be off. So this is infinity. So let's don't talk about that, right? You already cut out. However, if I put a PMOS, when would the PMOS cut off? Or when the R on will go very high? It's the opposite, right? So your V in is small, then your R on of PMOS will be very high. Now the beauty of the transmission gate is you put two in parallel, right? So if I have a parallel resistance, one look like this, the other one look like that. The composite resistance is here, right? You take whatever is minimum. That make sense? Okay, so that is the bottom line. So you do this R on N in parallel with R on P, right? So one is R on P, the other is R on N. So you do two in parallel and you roughly get that like this. Okay, so you can see that you are kind of capped with the particular bound. In real life, do you want this composite resistance to be as constant as possible, or you're okay to have this difference? You want this to be as flat as possible, right? But unfortunately, you can see there's a little bit blip in the middle, right? Yeah, that's where the two things kind of maybe combined, and depends on what's the threshold voltage and what's your VDD, right? So more and more, so you do need to simulate, so it's not just the transmission gate is gonna solve all your problem. So depending on technology that you're gonna have, you wanna simulate the whole thing and watch out, especially the middle part. Why is the middle part that you worry usually the most?
Both of them is going to be.
Because both of them are kind of moderate. When being is very high, which transistor is better? When being is very high, PMOS will be doing a very good job, right? Because the R will be low. When being is very low, you have a MOS to help you. It's always the middle guy. So the MOS is a little bit. PMOS, a little bit. You have two a little bit in parallel. Maybe you are still just a little bit so the middle part usually you need to be a bit careful, right? Especially, as I said here, multi-scaling will make it worse, right? Because you see the VDD is smaller, so it will be compressed. You will compress this, right? So your VDD is really low, and then remember the VTH does not scale together with VDD, right? Remember I said that in the technology class. They don't scale together. If you scale together, you are probably okay. The problem is that your VTH cannot keep scaling down. You only scale down your VDD, so you make the mountain here in the middle just like a volcano, and it can erupt, it can burst in the middle, right? So just be careful. This has become more and more of an issue, in the low power supply, especially in the advanced nodes. Okay. Any question? If not, let's take a short break right here. And when we come back, we'll continue.